In this video, we're going to multiply and divide radical expressions. In order to multiply radical expressions, we'll follow these simple steps. We'll multiply terms that have cleared the radical by each other. Then we'll multiply the radicands together. Remember, the radicand are the terms that remain under the radical sign. Then we will simplify, and here is the basic rule. You can see that if p is multiplied by some root of u, which is multiplied by q times some root of v, the terms that are outside of the radical will be multiplied by each other. So p times q will be multiplied. And since the radicands have the same index or root, those radicands can be multiplied together and put under one radical sign. So this is pretty much the reverse of what we talked about for product rule. With product rule, we started with factors under the radical and broke them apart. Now we're starting with terms that are broken apart and putting them back together. We can only do this, though, if the index is the same index for the individual radical terms. Let's see how this all works. So to multiply binomials with radicals, we will use many of the same properties that we used for other products involving binomial expressions. We will multiply terms outside of the radical signs by each other, and we'll multiply terms remaining under the radical sign, those are the radicands. We'll multiply radicands by each other. So how that works, for example, number 1, you'll see that the square root of 3 is a term under a radical. Since 3 is the term under the radical, 3 will then be multiplied by this other 3 that also is under the radical. So we are using the distributive property here. Terms that are outside of the radical get multiplied with terms outside of the radical, but terms under the radical are multiplied by other terms under the radical. For the first distribution, terms that have cleared the radical are 1 times 1, so that's just 1. Terms under the radical are 3 times 3. So 1 times square root of 3 times 3 is the same as 1 times the square root of 9. Next, we're going to distribute square root of 3 times negative 2 square roots of 5x. 1 is the term that has cleared this radical, so 1 is multiplied by negative 2. That would give us negative 2. Then 3 is multiplied by the term under the other radical. So that's 3 times 5 times x. That is the square root of 15x. Notice how we still write that product under the radical sign. So we end up with 1 times the square root of 9, which is the same as 1 times 3, minus 2 square roots of 15x. 15 has factors of 3 times 5, and since neither one of those factors is a perfect square, there's no way to simplify that. So our final answer then would be 3 multiplied by 2 square roots of 15x. Now there isn't any way for us to combine these because they are not like terms. In example 2, we have 5 square roots of 2 multiplied by 7 square roots of 12. So we have terms that have cleared the radical. 5 times 7, that would make 35. The terms under the radical are 2 multiplied by 12. So that becomes square root of 24. We might think that we're done at this point, but we should explore the number 24 a little bit further to see if it has any factors that are perfect squares. So we want to think about taking 24 and dividing that by prime numbers, such as 2, that gives 12. That could be divided by 2, that leaves us 6. That can be divided by 2, which leaves us 3. And that can be divided by 3, which leaves us 1. So 24 really could be 4 multiplied by 6. So remember, these terms are really still under the square root sign. This gives us now 35 is multiplied by the square root of 4 times the square root of 6. That means 35 is really being multiplied by how much is the square root of 4? That would clear as 2. So square root of 4 is simplified as 2, but we know 6 can't break down except for 2 times 3, and there are no perfect squares there. So we keep square root of 6. 35 times 2, those numbers have cleared the radical, so we can multiply and get the product, which would be 70 square roots of 6. That's our final answer. So notice how we often are using this factor ladder to help us break down our radicands into perfect squares because we're working with square root. For example 3, we have 3x times square root of 45x cubed multiplied by 2 square roots of 2x to the 7th. So the terms that have cleared the radical are going to be 3x multiplied by 2. That gives us 6x. Now we're going to multiply the terms that are under the radical. Because these are both an index of 2, in other words, square root, that's what's allowing us to multiply those radicands together. So I know I'm going to still have some product under the square root. 45 times 2 makes 90. X cubed multiplied by x to the 7th, that looks like product rule. So far we have 6x times the square root of 90 times x to the 3 plus 7. That gives us 10. So you do have to think back to some previous lessons with exponents in order to work these problems. Now we're ready to take 90 and break 90 into its prime factors. 90 is an even number, so I could start by dividing with 2. That gives us 45. Dividing by 5, I have 9. Divide 9 by 3, that leaves 3. Divide 3 by 3 again, that leaves 1. So I do have a pair of 3's to give me the perfect square 9, and then these leftovers, 2 times 5, will make a product of 10. So I have square root of 10 and square root of 9. Now that gives me 6x times square root of 9 times square root of 10. And do you remember what we did with our variable bases? We're taking this exponent of 10 and dividing by the index, that is the root. So 10 divided by 2 is 5, remainder 0. So that tells me the base of x will clear the radical with an exponent of 5, and none of that base will remain under the radical. So let's simplify what we can. We still have 6x, but we know that multiplication of square root 9 is the same as multiplying by 3, because 9 was a perfect square. There's nothing more we can do with square root of 10. That remains under the radical. And x to the 5th was a term that cleared the radical. So we need to put everything in its standard form. Terms that have cleared the radical are written first. So I've highlighted all the terms that have cleared the radical. 6x multiplied by 3 multiplied by x to the 5th. So 6 times 3 would give us 18. X multiplied by x to the 5th. Remember, that's x to the 1 plus 5, which is x to the 6th. The only term remaining under the radical here is the square root of 10. So our final answer is going to be 18x to the 6th multiplied by the square root of 10. For example 4, this pattern might look familiar to you. These are binomials. Do you remember FOIL or some type of distributing? That's what we're going to do here with our radical terms. Really, the only rule you have to remember is terms outside of the radicals get multiplied together, terms under the radicals get multiplied together. So with square root 6 times square root 2, both these numbers are under the radical. So the square root of 6 times 2, or square root 12, is the product. Now we'll take square root of 6 and multiply that by minus square roots of 10. So a positive times a negative means we are going to subtract this next product. Both 6 and 10 are under the radical, so 6 times 10 would leave us 60 under the radical. Next, we'll distribute the negative 15 that's under the square root. So square root 15 times square root 2. Again, negative times positive means we will subtract the product. 15 times 2 would be square root of 30. Our last distribution, negative times negative, means we're adding this last product. 15 times 10 means we have 150 under that radical. So notice 12, 60, 30, and 150. Those are all different numbers. So at first glance, none of these are going to be combined. But what we really need to be thinking about is, can we simplify any of these terms before we think about trying to combine any of those terms? So maybe 12 is a quick one to start with. What times what would make 12? And more specifically, is there a perfect square that 12 has for a factor? Like 4 times 3 would be really nice, because that is the same as 2 square roots of 3. So if you're not able to do it that way, you can take 12 and start dividing by prime numbers, and eventually you'll get the same answer of 2 square roots of 3. So I think 60 might be a good candidate to go ahead and make our factor ladder for 60. So starting with 60, I'll divide by 2 to get 30. I'll divide by 2 to get 15. I'll divide by 3 to get 5. I'll divide by 5 to get 1. So here's a pair of 2's. So I know 4 and 15. And remember, those terms are under radicals. So I'm subtracting square root 4 times square root 15. Well, I know that's the same as 2 square roots of 15. Notice that these first two terms do not have a common radicand, so I'm not going to be able to combine those. Let's move on to the next radicand, 30. I can divide that by 5 to leave 6. Divide 6 by 3 to give me 2. Divide by 2 to get 1. So I don't have any pairs that are the same. So that's going to remain minus square root of 30. We can't do any better than that. But sometimes you don't know that until you go ahead and try to work it out. Last, 150. Let's see how that's going to simplify. It ends with 0, so I know it's divisible by 5. 5 goes into 15 3 times, and into 0 no times. So 30 is divisible by 5, leaving 6. And we know 6 is divisible by 2, leaving 3. Divide by 3 leaves 1. So here we did form a perfect square of 25 multiplied by 6. So we can add at the end here square root 25 square root 6. That means we're adding 5 square roots of 6. Did that help us at all? We've got square root 3, square root 15, square root 30, square root 6. None of those are like terms. However, they are simplified. So this is the answer we want. This is the form of the answer we're looking for. So I'll just highlight here in yellow what the final answer looks like.